Imagine a vast cosmic sea, a dark expanse where the seeds of stars and planets are just beginning to stir. This is not a scene from a science fiction movie, but a glimpse into our own cosmic backyard over 4.5 billion years ago. The story of Earth begins in this ancient chaos, within a swirling cloud known as the solar nebula. From this cloud of gas and dust, bound by gravity and stirred by the laws of physics, a process began that would eventually see the birth of our solar system, including our own planet, Earth. What might seem like a tranquil history was, in fact, marked by violent collisions and incredible transformations, events that shaped not just a planet, but the future home of a myriad of life forms. This journey from cosmic dust to a structured, dynamic planet is not just a story of astronomical phenomena, but a profound narrative about the origins of life itself, setting the stage for a saga that spans billions of years. It's a tale of how from the simplest elements the most complex systems known to science emerged. In the vastness of space, the solar nebula was a cloud of gas and dust left over from the explosion of a previous star. It was the raw material for our solar system. About 4.6 billion years ago, a disturbance, possibly from a nearby supernova, caused the nebula to collapse under its own gravity, initiating the birth of the Sun and the planets. As the nebula collapsed, it began to spin, forming a flat, rotating disk. This disk was the cradle of the solar system. In the center, the Sun was born, fiercely igniting from the compressing gases reaching nuclear fusion temperatures. Around it, particles collided and stuck together, forming larger bodies in a process known as accretion. The dance of particles in this protoplanetary disk was a delicate balance of gravitational attraction and momentum. Over millions of years, these particles formed the planets, including Earth. This process was neither smooth nor peaceful, characterized by frequent collisions that would significantly influence the newly forming bodies. During the early stages of the solar system, Earth formed through the process of accretion, where dust and rock floating in space gradually came together due to gravitational forces. Over time, these small particles collided and merged, creating larger and larger bodies, until a planet-sized object emerged. This early Earth was a molten ball of fire, continuously bombarded by other space debris. Each collision added more mass to Earth and contributed to its internal heat, which was crucial for the later processes of differentiation and the creation of a magnetic field. This period was chaotic, marked by relentless impacts that would eventually lead to a critical event, the formation of the Moon. The intensity of these collisions is hard to overstate. One such colossal impact is thought to have been with a Mars-sized object named Theia. This event is theorized to have been so powerful that it led to the formation of the Moon from the debris scattered during the impact. This moon-forming event was pivotal in stabilizing Earth's tilt and rotation, which would later be crucial for the development of life. As Earth grew and its internal heat increased due to radioactive decay and residual heat from accretion, it began to differentiate. This means that Earth's interior started to sort itself into layers based on density, a core, mantle, and crust. This process was crucial for setting up Earth's geologic and magnetic properties. The heavier elements like iron and nickel sank towards the center, forming the dense metallic core. This core is responsible for Earth's magnetic field, created by the movement of molten metal within it, which acts as a shield against solar and cosmic radiation, protecting the budding atmospheres and potential life forms. The lighter materials, such as silicon and oxygen, floated to the surface, forming the crust. This crust is not a single, unbroken shell, but comprises several shifting plates. Their movement, driven by the heat from the core, causes earthquakes, volcanic activity, and has a significant role in the carbon cycle, crucial for life on Earth. Following Earth's differentiation, the next significant phase was the formation of the atmosphere and oceans. Initially, Earth's atmosphere was likely thick with volcanic gases, including water vapor, carbon dioxide, and ammonia. These gases were emitted by the intense volcanic activity driven by Earth's hot interior. As the planet cooled, water vapor began to condense and fall as rain, gradually filling the basins to form oceans. This process not only created the hydrosphere, but also started the long process of regulating Earth's climate system. The early oceans were a cradle for the next monumental stage in Earth's saga, the emergence of life. The transformation of the atmosphere continued with the emergence of life, particularly with photosynthetic organisms that began to convert carbon dioxide into oxygen. This biological revolution, known as the Great Oxygenation Event, dramatically changed the composition of the atmosphere, making it more hospitable for a wider variety of life forms and leading to the biodiversity we observe today. As the newly formed Earth continued to evolve, its surface began to cool, allowing for the formation of a solid crust. This crust, however, was initially very thin and frequently punctured by volcanic eruptions, which continued to shape the planet's surface and atmosphere. The cooling of Earth's surface was crucial for the stability needed to sustain long-term biological processes. The solidification of the crust also marked the beginning of the geological activity that would create and transform the continents. Plate tectonics, the movement of these massive crustal plates, began to rearrange the face of the planet. This not only influenced the physical landscape but also impacted the climate and environmental conditions, setting the stage for future ecological developments. The cooling period also had significant implications for the climate. As the planet cooled, more stable and varied climates began to emerge. These varying climates played a crucial role in the evolution of life, providing a range of ecological niches that could be exploited by different forms of life. This variation is a key factor in the diversity of life we see on Earth today. The stage was set for perhaps the most intriguing chapter in Earth's history, the rise of life. The exact origins of life remain a mystery, but it is believed that about 3.8 billion years ago, the right conditions allowed for the formation of simple life forms. These primitive organisms were likely based on RNA molecules, capable of storing and transmitting genetic information. Life began, most scientists conjecture, in the protective environments of Earth's early oceans. Here, shielded from the harsh solar radiation by water and possibly by volcanic ash clouds, these simple organisms began to replicate and evolve. Over countless generations, they became more complex, eventually leading to the development of DNA, the molecule that is the basis of all modern life. This early life was microscopic and simple, but it set the foundation for all future life on Earth. As these organisms evolved, they began to impact their environment significantly. The production of oxygen by photosynthetic bacteria changed the atmosphere, making it possible for more complex life forms to develop, a process that would eventually lead to the biodiversity observed in the Phanerozoic eon. The history of Earth is not just about its past, it is a continuous story of change and adaptation. The planet's environment and the life it supports have evolved together in a complex dance of geological and biological processes. Earth's surface continues to be shaped by the dynamic forces of plate tectonics, climate change, and biological evolution. These ongoing processes are crucial for understanding not only Earth's history, but also its future. For instance, the study of past climate changes such as ice ages and warm periods helps scientists predict how current climate change might affect our planet. Similarly, understanding the mechanisms behind mass extinctions and biodiversity crises in the past provides insights into how to protect today's ecosystems. Moreover, human activity has become a significant geological force in its own right, altering the planet's systems at an unprecedented rate. This adds a new layer to the saga of Earth, where understanding our impact and how to mitigate it is crucial for the continued health and stability of our planetary home. Earth possesses a set of unique traits that make it exceptionally suited for life. One of the most significant of these is its liquid water, a vital ingredient for life as we know it. Earth's perfect distance from the Sun ensures that its surface temperatures are stable enough to keep water in liquid form, a rarity in the solar system. Additionally, Earth's magnetic field, generated by its molten iron core, protects the planet from harmful solar radiation. This magnetic shield not only preserves the atmosphere, but also ensures that the surface remains habitable. Without it, life as we understand it could not exist, as solar winds would strip away the atmosphere, just as they have done on Mars. Moreover, Earth's geological activity, including volcanism and plate tectonics, plays a critical role in recycling nutrients and shaping diverse habitats. This geological dynamism ensures a continual renewal of surface conditions, which has been crucial in fostering and sustaining biodiversity throughout Earth's history. The story of Earth is an epic saga of transformations, driven by astronomical, geological, and biological processes. From a swirling cloud of cosmic dust to a vibrant, life-sustaining planet, Earth's journey is a testament to the complexities and wonders of the universe. This tale is far from over. Earth continues to evolve, with each geological and biological shift influencing the future trajectory of this dynamic planet. As we look to the future, understanding Earth's past and present becomes crucial. It not only helps us appreciate the fragility and resilience of our home planet, but also guides us in making informed decisions to protect and sustain it. The continued study of Earth's history is not just about satisfying human curiosity, but ensuring a livable planet for future generations. In this grand narrative, every rock, every gust of wind, and every creature plays a part. It is a story that involves us all, one where we are not just observers, but active participants. By learning from Earth's past, we can help shape its future, continuing this billion-year journey towards sustainability and coexistence.